Hello everybody, welcome to week 5's board review lecture on key high yield topics. And this one is definitely high yield. Boards love this one. It's the Renin Angiotensin Aldosterone cycle, the R2A cycle, or the RAAS cycle. Let's go. This will be on your midterm next week. So it's all review for you, right? So this should be very easy for you. Let's start off with this question. What condition of the body fluid compartments does this drawing represent? Okay, don't look at the answer down there. So water, solute. It could be sodium if you want, but just any osmolyte. Sodium is by far the most common in the extracellular fluid, but potassium is by far the most common in the intracellular fluid. So what do we got here? What's the ratio between salt and water? Well, we can already see there's 10 water molecules and there's 5 sodium or solutes. Same over here. And so is that normal? No, we said that all of these compartments like to have the same ratio between salt and water, or solute in water. In other words, they like to have the same osmolarity or osmolality. So this is no good. So now the question, is it hyperosmolar or hypoosmolar? Remember the solute rule. So if you have low solute and high water, this is hypoosmolar extracellular compartment or extracellular fluid of the extracellular compartment. And it's uncorrected because everything is cool inside the cell here, the intracellular compartment. There's an equal number of solute to water. So this has to correct, right? Great. So that leads us to this topic. There's two types, or the two big causes of hyponatremia, or a hypoosmotic extracellular fluid, is SIADH, syndrome of inappropriate ADH secretion. Too much ADH is secreted for various reasons, and we know that ADH causes reabsorption of free water, so ADH would cause this. We have too much free water floating around here compared to solute. So that's one thing that would cause this. In fact, this is called, because water is diluting the solute. Sodium is, again, what we're really talking about. It's not that we don't have enough sodium. We have too much water. So that's called a dilution hyponatremia if we're talking about sodium. Another condition is primary adrenal insufficiency. Probably the most common type is Addison's disease. That's an autoimmune cause of primary adrenal insufficiency. So no cortisol is secreted. And remember, from endo, there is a magnocellular neuron brake put on magnocellular neurons by cortisol. Cortisol inhibits magnocellular neurons from over-secreting antidiuretic hormone. What are the AKAs for antidiuretic hormone? Vasopressin, arginine vasopressin. Vasopressin, arginine vasopressin, or AVP. You got to know those those AKAs. So there's a brake put on there. Magnocellular neurons are hyperactive. They'd way over-secrete ADH if they were allowed to, but they're not. And we always have a certain basal amount of cortisol floating around all the time. And so it kind of puts a brake on magnocellular neurons. If you take off that brake in a condition that destroys glomerulosa cells in the adrenal gland, remember, glomerulosa cells secrete aldosterone. One more layer down, fasciculata cells, right? GFR, glomerulosa cells, fasciculata cells, reticularis cells. So primary adrenal insufficiency destroys the adrenal cortex, all of it. And so you can't secrete any of those things, including cortisol. So no cortisol, no magnocellular neuron brake, and ADH gets oversecreted just like it did here in syndrome of inappropriate ADH secretion. So they both do the same thing. And again, if you and we know ADH binds to principal cells, right? And it causes the implantation of an aquaporins 2 channel. And I have no idea why that decided to come on. But yeah, so you get the overabsorption of free water. Okay, what's going on here now? Okay, good. So that's kind of our little intro. But let's get into the R2A system now. So yeah, it's a dreaded system. Physiology students and endocrinology students don't like it, but I think you should have it down. We went over it really hard in SysPhys, and I'm not sure, I can't remember if I went over it in Endo with you or not, but let's go over it. Here's the books I used to build this lecture with. All board books, chiropractic board books, except there is no dedicated endocrinology book. So I always go with Goodman's, which is the best, one of the best endocrinology books. Anyway, who cares? Let's go. Let's meet the R2A system. So who is it? What is it? What's the story? What are the AKAs, first of all? R2A I like to use. Probably the most popular is the RAAS, R-A-S, Renin Aldosterone system. This is in physiology books, use this one the most, Renin Angiotensin Aldosterone system. But R2A, I've just always used that one. You can't live without this system. You have to have this or you will die. A few days you'll stay alive. Why do you die? Salt wasting. No aldosterone, can't reabsorb salt from the pre-urine or the tubular fluid of the nephron. Water, you pee out the salt, you can't reabsorb it, and you get like that first slide there. You become your extracellular fluid, including your blood and your interstitium, becomes very salt poor. In other words, hyponatremic or hypoosmolallic. Great. So you got to have it. It's a very widespread system. That's why it's always such a big lecture. So usually the whole week we lecture about it. It involves the kidneys, the brain, the adrenal glands, the arterioles, and the heart. Different areas of the brain, like magnocellular neurons, the RVLM, what else comes to mind? The vasomotor center is that. The thirst center. So yeah, it's all over the place. There's 3 main functions that this thing does. Number 1, it raises blood pressure and blood volume if for some reason it has fallen. So you could say it defends against hypotension or hypovolemia. Number 2, it defends against hyperkalemia. So it can decrease serum potassium levels if they get too high. Remember, those are very dangerous, right? Hyperkalemia can kill you. It can trigger ventricular fibrillation. Fun fact, hyperkalemia, the deadly hyperkalemia, is the most common cause of kidney failure. Typically secondary to what? You can see the Gillard question, can't you? Long-standing diabetes, whether it's treated well or not, and hypertension. Number 3, so this one is indirect, but it indirectly defends against hyponatremia. So that's low salt in the ECF. So how does that work? Well, we kind of talked about it already. So if you have not enough salt compared to water, we need to rectify that situation. So to fix the extracellular hyponatremia, how do you do that? Well, the cells are the ones that do this. So the cells will take up the water, because there's 2 ways we can fix this. We can either add salt or solute to it, or we could take away the water to it to fix the ratio. And in this case, the cells soak up that water. That's called a water shift. So to fix hyponatremia, water shifts into the cells, and the problem is solved. And now we have a proper normal osmolality out here. Great. But we've done two things. If you steal water out of the extracellular fluid, what's that going to do to blood pressure? Remember, extracellular fluid is inside the bloodstream and the interstitium. If you steal water out of these things, well, you're going to have hypovolemia and hypotension. Okay, we have another problem with all that water coming in to the cell as well. So I guess we'll look at that on the next slide. But yeah, hypovolemia then will stimulate our R2A system into action. And that's the whole point of the R2A system, is to fix hypovolemia and or hypotension. Pretty hard for hypotension to exist without hypovolemia. It can well, let's not get into the weeds here, but it can. But for this lecture, hypovolemia, hypotension is one and the same. We saw that little box already. Great. How does hyponatremia cause hypotension? So I guess we're continuing. The hyponatremia makes the extracellular compartment, we said this already, too watery. We said this. Yeah, or hyperosmotic. The body won't tolerate this, and we already said we're going to move water. What's the fix? We're going to move water into the cell. So we've already kind of talked about this in opening. Therefore, via osmosis, water will move from the extracellular fluid compartment, like the arrows are showing you, into the intercellular compartment. And the extracellular fluid compartment's osmolality is normalized. Great. But same thing as last slide. The extracellular fluid compartment's volume has shrunk. Because why is the volume shrunk? The waters went inside the cell. And that's going to cause our hypovolemia or hypotension. So, and the other thing we didn't mention in the last slide, what happens to the cell? The cell is not happy because it's stressing. It's filled up with water. See, look at this slide. So extracellular fluid is fine, but the intercellular fluid is not fine. There's too much stuff in here. And I should have made this cell expanded and stretched and blown up. And this has to be corrected quickly. How do we fix the hypotension? Well, that's what we're going to talk about next. I think we just talked about this already. Danger intracellular edema has occurred. This is kind of a fun fact slide about the cells of the body when this happens. They will actually start dumping out intracellular ions slowly out of the cell to draw water out of the cell. And by that point, things are normalized out here, and the extracellular fluid can tolerate the cells starting to dump some osmolytes out here to draw water out. But it takes 6 to 24 hours to do that. And so the cells, especially brain cells, can be damaged if there's way too much water in here. Yeah, so it takes 6 to 12 hours. And yeah, that's the story. You could die if this is severe from hypotonic encephalopathy, where basically the cells have taken up so much water, the brain cells have taken up so much water they explode and you die. You can't fix the brain cells, right? What's the fix for the hypovolemia? We said R2A system will turn on, and via aldosterone and ADH, it'll cause the reabsorption of free water, salt and free water. And we'll see how that works. That's where we're kind of going next. But that's the fix. Our R2A system will correct the hypovolemia by adding more water to the extracellular fluid. All right. What directly activates it? And I apologize for these slides. These are brand new slides that have been put together over the last week. So this is the first time I've ever given this particular lecture with these slides. So what directly activates the R2A system? So low blood volume, we said this already. Moving through, specifically though, we didn't talk about this. Low blood volume, so what? It's the afferent renal arteriole that senses the hypotension. And remember, there's cells here called juxtaglomerular cells. These little kind of turquoise or bluish color cells. They're modified smooth muscle cell that lives in the wall of the renal afferent arteriole. Remember, afferent arterioles feed the glomerular capillary, aka glomerulus, and we have the efferent arteriole here. But yeah, low blood pressure will stimulate these cells to release a hormone called renin. And that's these little red and or yellow dots. That's renin. We'll talk about what that does in a bit. Okay, what else does it do? It increases postganglionic sympathetic input. So that's another thing. What can set this off? So low blood volume sets off these juxtaglomerular cells directly. And then increased postganglionic sympathetic input. So remember the renal nerves. That's a postganglionic sympathetic fiber, ultimately coming from the lateral horn of the spinal cord. And it plugs directly into these juxtaglomerular cells. And if you get a strong wave of action potentials coming down here, it can directly stimulate renin, even if the pressure is normal here. So sympathetics, postganglionic sympathetics, can also stimulate the release of renin. Usually it's the carotid sinus. The baroreceptors in the carotid sinus detect the hypotension, and they allow the vasomotor center to send a signal to the lateral horn of the spinal cord, which is where the sympathetic chain starts, right? Those are the start of preganglionic sympathetic fibers. And that's where the flow of sympathetics comes from. But the other thing that can do this is stress. If you get really stressed out, you can start to send signals down to the lateral horn of the spinal cord and start increasing sympathetic flow. And you can get the release of renin even though your blood pressure is not high. And this will make your blood pressure high. So that's one of the mechanisms that stress makes hypertension. What else can do it? So decreased GFR. What's GFR? No, well, we use it for zona glomerulosa, zona fasciculata, zona reticularis, but no, that's glomerular filtration rate. That's the speed of the river, the speed of the tubular fluid moving through the nephron. If you get a decrease in GFR, that is going to activate macula densa cells. Now we can see macula densa cells here. This is the end of the thick ascending limb of Henle here. And if they sense decreased sodium chloride, which happens if you decrease the GFR, remember the proximal convoluted tubule cells they pick. If the river slows down too much, if the GFR slows down too much, they get too much time to pick out salt, sodium chloride, and the filtrate becomes not so salty. And by the time the filtrate reaches these macula densa cells, it's very hypotonic, and it drives these things crazy. They send a PGE2, prostaglandin E2 message to the blue cells here and say, hey, secrete renin. They can do this even if there's no hypotension here. So they can do that independently of the pressure inside the afferent arteriole. So important slide right here. All good with that? A little more complicated, we could get a little deeper, hypotension or low blood volume. What are some of the causes of it in general? Well, obviously a hemorrhage. If you're leaking, if your blood vessels are leaking somewhere, that's going to decrease your blood pressure, activate the R2A system. If the pump that pumps your blood is faulty and failing, like in cardiomyopathy or heart failure, you're going to have a decreased output out of the heart, or decreased stroke volume, or decreased ejection fraction. Decreased blood out of the heart is going to decrease blood pressure, turn on the R2A system. The nephrotic syndrome, remember that? And the nephritic syndrome. The nephrotic syndrome in particular, remember that's a condition where the podocyte foot processes are damaged. Remember, podocytes are very negatively charged. Albumin is very negatively charged. And the podocytes keep albumin from getting in the filtrate. Right? Albumin is not filtered. But in nephrotic syndrome, these podocytes are damaged, and albumin can get in. And if you lose albumin from the bloodstream, there goes your colloid osmotic pressure. That's your sucking force that pulls extra interstitial fluid and waste from the interstitium into the distal capillary. It's gone. And so you can't reabsorb the extra interstitial fluid. And you're going to swell. But more importantly, you're going to not have enough fluid in your blood. And that's going to decrease blood pressure. And that'll activate the R2A system. Nephritic syndrome, remember from renal fizz what that is? That's a chronic inflammation of the glomerulus, especially its endothelial cells in the basement membrane, and it makes it stiff, and that decreases GFR. And if you decrease GFR, you're going to decrease salt content in the tubular fluid. That's going to drive macular cells insane. They're going to stimulate via prostaglandin E2. They're going to send prostaglandin E2 messages to their next door neighbors, the juxtaglomerular cells, to release renin. Activates the R2A system. Chronic diarrhea, you lose water. That decreases blood pressure. R2A system. So these are all kind of low blood pressure syndromes. What about some mechanical problems? Well, the renal artery feeds the kidney, and it feeds all the nephrons. It feeds all the afferent arterioles. So if you get a kink of the pipe, a pushing of the pipe, a narrowing of the lumen, all that stuff will act like a beaver dam and cause downstream decreased pressure. So here's a couple examples. So here's a renal artery cross section. We can see what's going on. Renal artery will feed all the nephrons, afferent arterioles. And if we block the lumen with atherosclerosis, fibromuscular dysplasia is a condition that can do that. Arterial sclerosis, especially atherosclerosis, which is a member of arterial sclerosis. Remember the three members of arterial sclerosis? What are the three members of arterial sclerosis? Three subcategories of arterial sclerosis. Atherosclerosis, the one we all know. Monkberg's medial sclerosis, and arteriolosclerosis, a condition that affects the arterioles. Pathology 101 there. All right, so any of these things. Here's an aneurysm, not a great example, kind of didn't even Photoshop it in, but there's an aneurysm coming off this descending aorta, abdominal aorta here, or this abdominal aorta has an aneurysm, and it's pinching, stepping on the renal artery. That can activate the R2A system. So, yeah, all that stuff. In this case, the kidney will think there's hypotension everywhere in the body. It doesn't know, so it secretes renin, and your overall blood pressure goes up until your kidney pressure becomes normal. So this kidney will have normal pressure, but the rest of your body will have hypertension. Got it? Great. We talked about this, but just here it is again, because I can hear you saying, what is the nephrotic syndrome again? How does it cause hypotension? So again, nephrotic syndrome, the podocytes are wrecked, so albumin can be filtered, and that decreases your capillary oncotic pressure. Remember this thing? So here's the proximal capillary, distal capillary. And there's two forces. There's a pushing out force. That's what? Hydrostatic pressure generated by what? The heart. Remember that's strong in the proximal capillary, but that pushing out force decreases as you go down the capillary. Then we have this constant force in yellow. That's the sucking force caused by, are called oncotic pressure. These are Starling forces, right? And this never decreases because it's caused by albumin. It's really just osmosis 101, where we have, this is a beaker, this is a semi-permeable membrane, this is the other side container of the beaker inside the vessel, interstitium is the other side, and the vessel wall here is the endothelium, is the semi-permeable membrane. And so the albumin would love to get out and equalize, by going into the interstitium, but it can't. So the only way to fix the inequity of salt to water ratio is to pull water in here to fix that problem. Remember that? Yeah. And so nephrotic syndrome, if you lose these little green albumin, you lose your little yellow sucking force. This will be maybe just the arrowhead. It'll have no power. And so you can't return fluid down here like you're supposed to. And therefore, your entire body is going to become swollen. You should know what that is. Anasarca. Pathology again. Anasarca. Yeah, especially down in the ankles. It's called dependent edema because usually you're standing and your feet are in a position of dependence. All right, that means they have to fight gravity for blood to get back. Yeah. And I mean, the main point here, if you have tons of fluid trapped in the interstitium and you can't return the fluid to the distal capillary, well, then your blood pressures, you're not going to have a lot of blood. You'll have hypovolemia and therefore hypotension as well. Great. What else can set it off? Hyperthyroidism. So increased T3, T4, mainly T3, right? T4 is converted into T3. That's the big one. So what does having too much T3 around does? It actually oversensitizes the receptors on juxtaglomerular cells. You can't see this in this picture, but we know that sympathetics release norepinephrine. Norepinephrine sinks into the tunica media and causes the tunica media to contract. So there's receptors for norepinephrine on all these juxtaglomerular cells. And so T3 oversensitizes them and makes them too grabby. So even if there's just a trickle of sympathetic input here, they grab every single little molecule of norepinephrine and react it. And so they're not supposed to do that. They're not supposed to be that sensitive. And so, yeah, that directly stimulates the release of renin. Primary adrenal insufficiency. Remember, this is Addison's disease is a subcategory of primary adrenal insufficiency. It's typically autoimmune related. 21-hydroxylase gets attacked, remember that? And that's Addison's disease. But Addison's is only the autoimmune subcategory of primary adrenal insufficiency because we have infectious, we can have cancerous, we can have blood vessel or aneurysm type. So, but anyway, primary adrenal insufficiency. Bottom line is the adrenal cortex is damaged and it can't make any of its steroids. No aldosterone, no cortisol, no DHEA, nothing like that. Okay? Am I not going to explain that to you? Well, if you can't make aldosterone or cortisol, then how's that going to set off the R2A system? If you can't make aldosterone, then you can't reabsorb salt. And so if you can't reabsorb salt from the filtrate or sodium, chloride will follow through Pendrin channels. But if you can't reabsorb salt, then your extracellular fluid, including your bloodstream, will be hypotonic or hypoosmolalic or have hypoosmolarity, however you want to say it. The ratio between salt and water, too much water, not enough salt, that'll cause low blood pressure and that will stimulate the R2A system. So that works. Plus the cortisol, remember we said that puts a brake on magnocellular neurons. We just described that. And so in Addison's, probably the most important one is there's no cortisol. And your blood pressure will drop like a stone, partially from the reabsorption of free water, which will dilute the blood and extracellular fluid. Let's see how that works. Okay, how does the whole story work here? So I tried to, because this is a a 5-hour lecture, right? So I'm trying to cram it down into something short. So I've tried my best here. Short story. How does this R2A system actually work? Now we kind of know what it does, but raises up low blood pressure, defends against hypotension. So once it gets stimulated by hypotension or by sympathetics, or whatever, hypotension we'll just use, juxtaglomerular cells release renin. We said this already. Into the afferent arteriole. And it's an arteriole, so renin is a hormone and it's loose, flowing through the bloodstream. Renin looks for its mate. It has a substrate to bind to, and its mate is a liver protein, which is floating around in our bodies right now. It's made all the time. It's called angiotensinogen. Renin, by the way, is a hormone and enzyme, a very interesting molecule, but it cuts a few amino acids off the end of angiotensinogen, which creates a short version of angiotensinogen, which is more active, and that's called angiotensin 1. Still doesn't do much for our purposes. But angiotensin 1 has a mate, and its mate is called ACE, angiotensin converting enzyme. And ACE is not floating around the bloodstream. ACE is anchored to the endothelium of capillaries that are mainly in the pulmonary endothelial capillaries. They're in other places of the body too. But angiotensin 2 finds its enzyme called ACE, and ACE does the same thing. It cuts a few amino acids off the tail of angiotensin 1, and that makes a new, very aggressive molecule called the dreaded angiotensin 2, which is wonderful if it's emergency and you're bleeding out. But if it's oversecreted, it causes all kinds of trouble. I call it the Tasmanian devil of enzymes. Angiotensin 2 is the main effector of the R2A system. Angiotensin 2 immediately recruits 2 helpers to help in its primary mission. What's its primary mission? It's to raise blood pressure. That's its job. Usually in the construct that blood pressure is low, but not always, right? Increased sympathetic tone or kidney failure. So angiotensin 2 activates 2 friends, aldosterone and vasopressin. So these 3 are the main activators or main effectors, I should have put in here, instead of activators, main effectors of the R2A system, with angiotensin 2 being the king. A few years ago, this was the big defensive line, which is destroyed now. But anyway, the 3 big effectors, there we go, of the R2A system are vasopressin, aldosterone, and the king, the bossa of the 3, although he's not doing so good this year, is he? Angiotensin 2. Great. And they accomplish the blood pressure lowering stuff, or blood pressure raising effects. Got it? Great. Angiotensin 2, let's talk him over. Let's see. He's on the loose now. And I cut all the kidney stuff out because we talked about that last week. So let's just get to what does angiotensin 2 do. So number 1, it causes vasoconstriction of arterioles all over the body. Venules a tiny bit, but I should have erased that because that's a very non-significant or insignificant function. It binds to arterioles throughout the body. This is the most important action that angiotensin 2, guarantee I'm going to test you on that. Angiotensin 2 circulates throughout the blood, and it's looking for its receptor. Its receptors, strangely enough, are called AT1 receptors. There are 4 different types of receptors. All we care about for this class and boards is AT1 receptor. And that's located, guess where? On the smooth muscle cells of arterioles throughout the body. So that's how this works. Angiotensin binds to the smooth muscle cell membrane, and that triggers, it can't go inside the cell membrane. Here's a picture right here. There's angiotensin 2. There's norepinephrine and ADH also known as arginine vasopressin, AVP. They all do the same thing. They trigger this secondary messenger system here. It involves PKC, not PKA, PIP, PIP2. We'll just call it an IP3 there. We won't worry about this. That's too deep for boards. But we should know that it stimulates a secondary messenger system. That goes in and it causes the release of calcium. And we know calcium causes the actin and myosin filaments to slide together, and that contracts the muscle. And if this is going on in 10,000 muscle fibers, it's going to make the muscle thick and it's going to narrow the lumen. And that's what we want to do, right? We want to narrow the lumen. Because if you narrow or vasoconstrict the lumen, that is, number one, that is going to act as a beaver dam for the rest of the body's bloodstream, and that's going to raise blood pressure. It increases afterload. The heart has to pump through that afterload, so the heart will be forced to pump more powerfully and faster. The lungs, you'll get tachypnea. The lungs will be working harder to keep up with the heart as well. That's going to raise blood pressure. Number two, what else does it do? It directly binds to our friends, the glomerulosa cells. Angiotensin 2 binds to glomerulosa cells. Oh no, this picture is back for the test. Glomerulosa cells, just like hyperkalemia, can directly bind to glomerulosa cells, and it stimulates mineralocorticoid release or aldosterone. I could say either one of those on test, but it stimulates aldosterone, right? Okay, so what? What does aldosterone do? Okay, we've been doing this in cis-phys and in endo. What does this thing do? So there's aldosterone. It's a steroid hormone. It can go through the cell membrane of a principal cell like a ghost. Its receptor is an MR receptor that lives in the cytosol. The complex goes into the nucleus, binds to a specific gene that's got a receptor for the MR aldosterone combo, and it does three things. It manufactures new epithelial sodium channels called ENaCs or ENaC channels. Kind of redundant, but I like to call them ENaC channels. It also makes RAAS channels. Those are renal outer medullary potassium channels. And it makes extra sodium potassium ATPases. Remember, these are on the basolateral surface. This is basolateral surface. This is the apical or luminal surface. So RAAS channels, ENaC channels are on the luminal or apical surface, and sodium potassium ATPases, extra ones, are put on the basolateral surface. Great. And then they do what they do. So once you put an ENaC channel in, the tubular fluid has way more sodium. Even though it's water rich, it has way more sodium compared to inside the cell, because we know the cells hate sodium. They always get pumped out. So sodium pours in and it immediately gets kicked out through these sodium potassium pumps. So now we got sodium, or we got kind of salty blood. Chloride will follow via pendrin in a beta intercalated cell, but let's worry about sodium right now. Also, if sodium is going out, we have, or coming into the cell being reabsorbed, we have potassium getting kicked out. What is getting kicked out? No, not excreted, not in physiology. It's really secreted. Urine is excreted from the renal pelvis. It's secreted. Remember that story? Great. Principal cells. So this might be updated from when you had it with me. I used to emphasize the connecting tubules in the proximal part, or the cortical part of the collecting duct. Turns out they're in the entire collecting duct. The density is higher in the collecting or the connecting tubule and the cortical portion of the collecting duct. But nevertheless, there's those principal cells. What do they look like? That's a principal cell right there. It's a little blue dot right here. See how that works? Yep, so they live connecting tubules, collecting ducts, super important for maintaining salt, potassium, acid base. That's not true. Acid base comes from alpha intercalated cells. So that one's kind of indirect, because aldosterone does stimulate that process as well. I think we talked about that last time. but water homeostasis as well. Yep, so everything I just said. So you can read through this. I just said the whole thing. You can read it, but I already explained it. Right, yep, sodium is removed, sodium potassium pumps, everything I said. Yeah. What about the chloride? Students always ask, well, where's the chloride come from? Because doesn't chloride always follow salt? It does, but it doesn't come through the principal cell. It comes from not the alpha intercalated cell, but a beta intercalated cell. And it specifically comes from an exchanger called pendrin. And pendrin, it depends on which textbook, how this works. It's now believed that there are mineralocorticoid receptors for aldosterone in these beta intercalated cells. That's kind of in the leading edge of research, but most of the traditional, like Guyton, doesn't acknowledge the existence of it. It just says that pendrin is a chloride bicarbonate exchanger, and that will suck in chloride because of sodium, kind of chasing sodium. Because when you pull sodium out of the pre-urine here, the tubular fluid, it makes this fluid very negatively charged. A little bit of potassium is coming in, but that's not enough to offset the amount of sodium that's going out. So we have a negative charge, and negative repels negative, so chloride is kind of driven down a kind of a negative gradient going that way. What's the word I'm looking for? Can't think of it right now. And then there's these little channels where these chloride bicarbonate exchange, or these little chloride channels where it comes out. So the only thing I want you to know for my test, I might say chloride chases sodium through what channel and what cell. So you should know what chases. It has to go through pendrin, which is on the apical surface, and this is a beta intercalated cell. Pendrin is a chloride bicarbonate exchanger, but we won't worry about that. I'd be happy if you know that story. And here's everything that I just said. Here's the basolateral surface has a chloride channel and an AE4 channel. I think we're getting pretty deep now for boards. But who knows, this could be a super hard question on boards. I did see some super hard physiology questions. So, all right, everything I said, let's move on. What happens when the blood gets too salty? Well, we know this. So a 1% increase in salt concentration will stimulate the release of ADH, antidiuretic hormone, also known as vasopressin, also known as arginine vasopressin. So extra salty blood, that means it's hypernatremic. It also means it's hyperosmolalic, or the osmolarity has increased because of the salt. But we have receptors that live in the third ventricle, the wall of the third ventricle. There they are. Specifically, these regions are called circumventricular organs. There's a whole bunch of them, but there's a few of them that are salt detectors. The Ovolt and the SFO, these are the exact CVOs that detect hyperosmolality, specifically hypernatremia. 1% will set them off. What do? So, and they're osmoreceptors, of course. So they detect increased osmolarity or osmolality. They have wires that connect right to the supraoptic nucleus and the paraventricular nucleus. And remember, there's magnocellular neurons in here, and they plug into those magnocellular neurons, and we know magnocellular neurons secrete antidiuretic hormone. So that's one way. We'll learn that the angiotensin II can bind directly to those magnocellular neurons that also stimulate the same process. Bottom line is they cause the secretion of antidiuretic hormone. Everything I said. Yeah, magnocellular neurons secrete vasopressin, whatever AKI you feel like using, travel down the posterior pituitary. Yep, note angiotensin II can bind to magnocellular neurons, so this is kind of doubled This is so important, this mechanism. What does the vasopressin do? We haven't talked about that. Well, we have, but you probably forgot it. So vasopressin, here it comes. That's the same as ADH. That can't go in the cytosol. This is a peptide hormone, so it needs a receptor that's on the cell membrane. So there are V2 receptors. You should know that. V2 receptors on the basolateral surface. And that's where vasopressin binds. So it stimulates the second messenger system. I think it's a cyclic AMP PKA system, but we won't worry about that in this class. But it stimulates this chain of dominoes falls, and the main effector goes in, and it stimulates the implantation and manufacturing, if need be, of aquaporins 2. Remember, aquaporins 2 really, they float around in a vesicle, and when vasopressin binds, it causes the vesicle to dock to the apical surface and release the aquaporins 2 channel. That's called translocation. It translocates, just like a GLUT4 transporter does in fat and muscle cells in response to insulin. The same thing here. So aquaporins 2 are water channels. And remember, the fluid right here, just coming out of the distal convoluted tubule, is very, very water rich. It's very hypotonic. Remember why that is? Somebody remembered the TAL cells, the tall cells, thick ascending limb of Henle cells. They're impermeable to water, yet they have a transporter, that sodium potassium 2 chloride channel, which sucks salt and potassium out of the fluid. And water wants to follow salt, but it can't. So the fluid, the tubular fluid, is very water rich, very hypotonic. So if I open an aquaporins channel, there's plenty of water here inside the cell, but there's tons of water molecules out here. So water molecules will go down its concentration gradient, and then there's aquaporins 3 and aquaporins 4 channels in the basolateral surface, so zips right on through. Great, wonderful. That's the story with that. Everything I just said. So water is basically chasing salt. It's being osmotically pulled down a concentration gradient. And then it gets into the we just understand it gets into the capillaries. The distal part of the capillary is where it goes via oncotic forces pulling it. So bottom line, angiotensin 2 stimulates the reabsorption of salt, and then indirectly stimulates the reabsorption of water, and it's the water coming in that will increase the blood pressure. What else does it do? We said this one already, but angiotensin 2 can bind to magnocellular neurons in the hypothalamus, and we already talked about that. Let's see, did I make a little cartoon of it binding? No, we're just talking about the osmoreceptors. But angiotensin 2 can directly bind to all these little cells here, these little green ones. Those are the magnocellular neurons, and yeah, that stimulates them. But the point is they directly bind, as we already said. Great. Angiotensin 2 finds its V2 receptor. We already said this already. Antidiuretic hormone, finds V2 receptor, causes reabsorption, and you know the rest of the story. What else can angiotensin do? It's a busy molecule. That's why it's the Tasmanian devil. It can go find the heart, and it can bind to its AT1 receptors on cardiomyocytes and stimulate them to contract more powerfully. We won't worry about the physiology of that. It can bind to the SA node and speed up its rate of depolarization, which increases the heart rate. It can bind to the AV node and decrease or inhibit decremental conduction. Remember, the AV node slows the signal. The wave of depolarization going from the atria to the ventricles is slowed down right here. That's called decremental conduction. So if we inhibit decremental conduction, the current isn't slowed down, and it zips right in here, and that will speed up the heart in and of itself. So you should definitely know angiotensin 2 binds to what 3 parts of the heart? cardiomyocyte, silent vertebral node, atrioventricular node. Great. What else does it do? Can it even do more? Yeah. It can go to the thirst centers. In fact, this is a powerful one. In fact, I had a bag of potato chips for lunch, and I'm thirsty right now. My hypothalamic thirst center is telling me to get some water, and unfortunately the water's downstairs. I forgot to bring it up, so I'll have to wait and be thirsty. But there's angiotensin 1 receptors for angiotensin 2 on the hypothalamic thirst center. What's the nucleus of that? What's the big deal with that? The CVO, circumventricular organ, there's one called, we know this already, it's the same ones, OVLT, and the SFO, subfornical organ vasculosum of the lamina terminalis, OVLT, thirst center. And it binds and stimulates it and makes you thirsty. It's a little more complicated than that, but that's good enough for us. And if you're thirsty, you will drink water. And if you drink water, that's going to be reabsorbed in the intestines and get right into your bloodstream and immediately boost up pressure. What else? Can it do more? Yes. It binds to mesangial cells, interglomerular mesangial cells. If you want to get technical, there's extra and intraglomerular mesangial cells. They're like these little starfish. Here's one of them between a couple glomerular capillaries here. And so angiotensin 2 can bind to this one, and it causes this starfish to contract and narrow, and that's actually going to, because there's other ones here, and when it contracts, it narrows these capillaries, and that's going to slow the GFR down, and that's going to allow more sodium and chloride to be sucked up by the proximal convoluted tubular cells. Bottom line, make the tubular fluid very hypotonic, very salt poor, and it's going to drive macula densa cells crazy. Macula densa cells will taste this, and there's transporters. I think they're actually sodium potassium 2 chloride channels here. It's not really a snake tongue, but I kind of like this. But when it tastes low salt, it goes crazy, and it sends prostaglandin E2 messages that act as a paracrine signaling, and it doesn't even need the bloodstream because juxtaglomerular cells are right next to it. And yeah, that stimulates the release of even more renin. We've talked about this, proximal convoluted tubule, picking out salt. How does that actually work out of the proximal convoluted tubule? Well, these proximal convoluted tubules, here's a proximal convoluted tubule cell right here. There should be no membrane right here. The author I don't know why he or she drew that, because these are the membrane, these are the wall of the proximal convoluted tubule. There's no layer like this. But anyway, the cell, you should definitely know who the transporter is, and this is the apical surface. We have a SGLT2 transporter, sodium glucose cotransporter 2, and it's a doubler. It takes, via concentration gradient, it takes sodium, which is here, and it also takes glucose. This is the same way as glucose gets reabsorbed. So an important transporter. Great. And then it goes through, the sodium just goes through that run-of-the-mill sodium potassium ATPase, or sodium potassium pump. Gets into the interstitium, not much of an interstitium, but it gets sucked into the capillary. And that's how that thing works. Covered all that. So great. It's going to get into diabetic medication, and this is, well, let's not get into that. But these are the targets of some diabetic medications to block the function of these. So you pee out glucose. If you pee out glucose, it takes the glucose out of your blood in people with chronic hyperglycemia. What else does it do? Could it possibly do more? Yes. It binds directly to chromophil cells that live in the renal medulla. Remember, the renal medulla has chromophil cells. What do they secrete? Catecholamines, especially epinephrine, and a lot of norepinephrine, a little bit of dopamine. These are the 3 catecholamines. I always ask a question like that. All the following are catecholamines except for blank. Great. So what? What does epinephrine do? it doubles the actions of angiotensin 2 on the heart. It binds to the SA node, the AV node, and the myocardiocytes as well. Does exactly the same as we discussed in angiotensin 2. Increase SA node firing, decreases or inhibits decremental conduction of the AV node, stimulates cardiomyocytes to beat more powerfully. It also stimulates arterioles to vasoconstrict in the body. So that's another function of angiotensin 2. That's a powerful mechanism right there. Decremental conduction, we talked about it. Don't need to say anything more about that, I don't think. We know that. There it is. Normally slows down the wave of depolarization, and that gives the atria time to contract. We don't want the atria and ventricles contracting at the same time, so we need to slow the signal down here. That's probably enough for you. I have another 50 slides left, but I think that's probably enough for you guys. Yeah, this is the whole story. This is everything we just covered, is this little chart right here. Let's go a little bit more, just a smidge, because let's just mention that people with heart failure or kidney failure, people who always have hypertension, they always have the R2A system on. And therefore, there's always the big three, always angiotensin 2, aldosterone, vasopressin. And these two, angiotensin 2 and aldosterone, they can damage the heart, they can damage arterioles, and they can damage the kidneys, the vessels, the small capillaries. How do they do that? They get in there and they cause a inflammation, a fibroblast heavy inflammation. And that fibroblast heavy inflammation, it scars up things like the myocardium, like the tunica media of arterioles, and like the glomerular capillaries of the kidney. So it's very important in people with heart failure that we have to use medication to decrease the amount of angiotensin 2 and aldosterone in particular if you want to live long. And so what does a heart failure patient do? Well, lisinopril. To slow down the progression, they must take medications like lisinopril, an angiotensin 2 and ACE inhibitor. It's called angiotensin converting enzyme ACE inhibitor. So what does that do? Well, it inhibits ACE. It binds to ACE and blocks it. So angiotensin 1 comes around and it can't be converted into angiotensin 2. And then we have ARBs. Usually these are taken together. ARBs, angiotensin 2 receptor blockers. So they block the receptor for angiotensin 2. So they let angiotensin 2 be made, or angiotensin 2 be made, but then it floats around and it can't bind anywhere because the receptors are blocked. So this would make it, I won't test you on this, but if it blocks the function, was it an antagonist? Are these ARBs antagonists or agonists? They're antagonists. They block the function. All right, and then there's mineralocorticoid receptor. And oh, there it is, isn't it? Antagonist. So it's a blocker again. All right, that's a good. We already covered that one. So let's stop it right there. So this is the cutoff. And next week there will be no lecture because I'm going to be making a test for you. Remember the test. It's going to be online. I'll probably open it up from Friday to Sunday. This quarter's kind of a mess because we have that professor's out for the whole quarter who's taking half of the class. And so we're just trying to get through this. But I'll warn you right now, you have to know your stuff. You'll probably try to make a little crib sheet or something to help you. But you're going to have to go fast because it'll be like 50 questions in 50 minutes, 1 minute per question. There'll be no going backwards. You go straight forward. We don't have the service where I can watch you, so you don't have to turn your cameras on. But yeah, good luck with it. You do have to know your stuff. All right, any questions? I've gotten 0 questions from you guys. And I have most of you in my endocrine class, so If you have questions over this, make sure you ask me. All right. See you later.